energy, then they just plug in. They're just going to plug in. Hang on 1 second. My Zoom just made a noise at me. I'm making sure it's still recording. All right. I'm not sure what that was all about. Anyway, if we let the physicists choose their units, I just lost my PowerPoint then. It wasn't. Huh. If I have time, I'll edit that out. Otherwise, apologies. If we let the physicists choose the units for mass, they're always just going to choose kilograms. That's the standard unit that physicists use. And velocity, physicists are pretty much always choose meters per second for velocity. So if you take a kilogram times meters per second squared, that's an energy unit that they just renamed. So this term here, 1 kilogram times meters squared over second squared, is a definition. We're not going to use that form of it. We're not going to use this equation at all. I just want you to know where that energy unit came from. It's just a combined unit, kind of like density, but it's more convoluted than that. So this is our most common conversion that we're going to use. Is it 1 calorie is 4.184 joules. I didn't mention too, calorie, this version of a calorie, this is actually not a nutritional calorie. Calories that you eat are actually kilocalories, but they don't get packaged that way in the US. If they're actually being careful in the way that they write their nutritional facts, they're supposed to write the units for the amount of energy, the amount of calories in your food with a capital C. Capital C for calorie is actually shorthand for kilocalorie. So I don't know how well you know your prefixes, how much you remember your prefixes, but a kilocalorie is going to be 1,000 times larger than a regular calorie. I don't know why they don't. I guess I shouldn't say that. I have my suspicions as to why they don't just put kcal on nutritional facts in the US. It's probably because Americans have a phobia of these metric prefixes. And so they just get around that by saying, well, a nutritional calorie is a kcal, but we're just not going to say kilocalorie because it's scary. Be that as may, if you go to other countries and look at their nutritional facts, they actually are usually labeled as kcals instead of nutritional calories like that. There's lots of other units for energy that you'll use depending on what field you go into. If you go into physics or electrical engineering, you measure all of your energies in terms of electron volts, which has to do with the amount of energy of moving a single electron up and down in the potential energy scale. If you go to mechanical engineering, you might use BTUs, which stands for British thermal units. If you go into the natural gas industry, they actually sell gas in terms of therms, and a therm is 100 cubic feet of natural gas. If you look at your utility bill, you'll see energy is being sold to you as kilowatt hours. All of these are just different ways of measuring the same thing. They're all just different measures of energy, but depending on what field you go into, sometimes it's easier to use some units rather than others. Some of these other ones that are more esoteric, barrel of oil equivalent. That gets used a lot in economics, actually. When you start talking about how much energy does an entire country or community use, if you put it in units of fossil fuels, you can take all of the amount of energy and turn it back into this is how many barrels of oil you would have to burn in order to produce this much energy. Which so that's kind of a weird one. Hopefully, it's getting more and more outdated every year, but it's still relatively common in some economics texts. And then in This one's right on the edge here. Tons of TNT is actually an energy unit that they use for rating explosions. So anytime you're talking about how large of an explosion something is, you can put it in tons of TNT so that there's something to compare it to. This is just kind of a fun look at how big different amounts of energy actually are. I'll let you look at this yourself, but I will point out that it's a log scale. So every one of these lines is 10 to the 3 times larger. So there's 1,000 joules, that's 1,000,000 joules, billion joules, etc. And so that's just kind of interesting to look at in terms of how much some of these different things produce in terms of energy. All right. So how are we going to actually measure this? Now that we have some units, and now that I've spent some time talking about other units, but it's always going to come back to joules and calories for us. And so the way that we actually measure some of these is we make use of a property of matter called specific heat. And specific heat it's a combined unit like density, and it's basically how much energy does it take to change the temperature of an object or of a material, right? So the definition is it's how much energy raises 1 gram of a substance 1 degree Celsius. Usually in Celsius. You could actually have specific heat and it's a Fahrenheit, but why would you do that? We stay away from Fahrenheit any way we can, right? Sometimes you hear this, the specific heat as applied to an entire object is called the heat capacity. So this is going to get really confusing because you've got specific heat and heat capacity are kind of similar terms. Neither of them is the same as just saying heat. Specific heat is the amount of energy it takes to change 1 gram 1 degree Celsius. Heat is the overall amount of energy that's changing hands. All right, so this equation right here is called the heat equation. And in this equation, the CP unit is our specific heat. It looks like it would fit with heat capacity, but the P is actually saying at a constant pressure. It comes from the physics definition of energy in gases, which if you take upper division chemistry, you'll see it again when you get to physical chemistry, probably your 3rd year in college. But so don't worry about what that P is. This whole term is specific heat. This term, delta T, delta always means change in, right? So this is change in, and it's capital T, so it's temperature, not time. Nothing about this has to do with time. Capital T is temperature. So there's our change in temp. And then our last term here is the mass of the object. So if we take the mass of the object times the specific heat times the change in temperature, we get Q. So what is Q? Well, if we look at the units here, our specific heat is energy per gram per degree. So if I erase this and look at energy, all right, our units, our specific heat was joules per gram degree Celsius. So mass is going to be in grams. Delta T is going to be in degrees Celsius. We actually look at how everything cancels out. Grams cancels grams, degrees Celsius cancels degrees Celsius. When we multiply all these together, we just get an energy unit. We just get joules. So this Q term is energy, and we call it heat. And so heat very specifically doesn't actually mean how hot something is in science. Heat means how much energy change hands in order to cause a temperature change. Heat is always talking about a change in temperature, not just something that's hot. You touch something and it's hot, that's not heat. It doesn't have heat. Heat specifically is a change in energy. All right, so let's do practice with that, and then we'll end this video, I think. All right, so here's an example. If you burn 1 gram of table sugar, it produces 16.5 kilojoules of energy. If all of that energy goes into 120 grams of water, what is the temperature change of the water? So for all these problems, anytime we have something changing temperature, you should be thinking this equation: Q equals mass times specific heat times delta T. This question is saying, what is the temperature change? So we're solving for delta T. We know Q is 16.5 kilojoules. We know specific heat is 4.184 joules per gram degrees Celsius, because that's just a given. It's on your conversion sheets. You don't have to memorize it. You just have to know what it means. Then last but not least, we need mass. Mass is given to us as well, right? Mass is 120 grams of water. So we look at this equation now, we have all the pieces that we need. All we're going to look at here is plugging everything in, except we do have to pay attention to units. Our Q is in kilojoules, which is fairly common. A lot of times we're dealing with large amounts of energy, but our specific heat was in joules. So we just need to do a quick conversion. So we can say, okay, every 1 kilojoule is equal to 1,000 joules. Get 16,500, or 1.65 times 10 to the 4 joules. Now we plug all that in. 1.65 times 10 to the 4 joules equals 120 grams times 4.184 joules per gram degrees Celsius times delta T. Just gonna clean this up. So all I do is plug in those numbers. Now it's just a little bit of algebra to solve for delta T. So delta T is equal to 1.65 times 10 to the 4 joules over 4.184 joules grams degrees Celsius. So joules are going to cancel out joules times 120 grams. Grams is going to cancel grams. So our units at the end are going to wind up being 1 over degrees Celsius, which we know from just how fractions work, that 1 over something, we took the reciprocal, then we took the reciprocal again. So we're just going to wind up with units of degrees Celsius at the end. So our final answer here, 1.65 E4 over 4.184 over 120. Delta T is 32.9 degrees Celsius. Keeping 3 sig figs, because we had 3 sig figs on our heat term. We had 3 sig figs on our mass. And we had 4 sig figs on specific heat. So we get to keep 3 sig figs at the end. So 32.9 degrees Celsius. All right. I think this video is probably long enough at this point. So we'll end it there. Your assignment today is to start working on some practice with these. Some of the trickier problems on that assignment, you are probably going to need to work in groups or work with Dr. Bedwell. And then if you still have questions, we can go over them tomorrow when I'm present in class. So have a good day today, and I'll see y'all tomorrow.